Structure and bonding of elements and compounds, Part 2. In Part 1 of this video, we developed a triangular space with the elements arranged along the top from the most reactive metal cesium to the left and the most reactive non-metal fluorine to the right. All possible compounds formed by the elements will now fall into the triangular space, the structure triangle. When non-metals bond with each other, we get small, self-contained molecules, substances that are already gases or will vaporize easily. These are called volatile. Don't confuse this with being reactive. Consider chlorine. Its 7 outer electrons are held by an effective nuclear charge from the nucleus of +7, as we saw in Part 1 of this video. As 2 chlorine atoms approach each other, they attract, and their 2 lone electrons pair up, filling the outer shells of both atoms. We now have a covalent bond formed by the attraction of the 2 electrons and the 2 nuclei. If a third chlorine atom approaches, there is no room for its electron in the outer shell of the atoms already there, so it is unable to bond. Thus chlorine, the element, exists as a set of independent diatomic molecules. The same form of covalent bonding occurs between any pair of non-metallic elements because the outer shells quickly become full. Thus, most compounds between non-metallic elements are volatile. That means that they evaporate easily or are gases. Here are some drawn on our triangle: molecular covalent bonding. We now consider 2 metal atoms which approach each other. As these sodium atoms approach, their electrons overlap and a molecule will form, because there is plenty of room in their outer shells. Such molecules do actually exist, for example in sodium vapor streetlights. However, as additional atoms approach, they too will be attracted in, because there will always be space in the outer shell of the atoms. So sodium, as an element, forms a closely packed 3-dimensional metallic lattice where the atoms are bonded by a sea of electrons in these partially filled outer shells. The loose electrons mean metals conduct electricity and heat very well. The non-fixed nature of the bonds means that the atoms can slide past each other, so metals can bend and melt very easily, but they will be difficult to vaporize. This form of bonding will occur between any metallic elements which have only a few electrons in their outer shell. Here is brass, an alloy of copper and zinc, for example, retaining the metallic properties of its elements. Thus, we can fill in the metallic bonding part of our structure triangle. With elements of group 4, carbon and silicon, there are 4 electrons in the outer shell and room for 4 more electrons, so 4 bonds will form. In this case, it's possible to build up 3-dimensional structures with the bonding going on forever. This is the 3-dimensional structure of diamond and silicon, where the atoms are covalently bonded in this lattice, making these giant covalent rock-like structures, solid at room temperature and very difficult to melt and vaporize. With carbon, we also get more flexible giant chains called polymers, particularly when it bonds with hydrogen, so we should add life polymers to this middle triangle. So far, these structures can be elements or compounds, with the compound having similar physical properties to the elements from which it is made. We now consider where the elements are very different. Take chlorine and a metal such as sodium. The effective nuclear charge holding the sodium electron is only +1 compared with +7 from chlorine, as we saw in Part 1 of this video. So the molecule will be highly polarized, with the electron pulled strongly from the sodium to the chlorine, leaving the sodium positively charged and the chlorine negatively charged. When the ions are packed in a 3-dimensional lattice, the structure is stabilized and we have ionic bonding. Because the ions have strongly fixed positions, ionic crystals are brittle, with high melting and boiling points. When dissolved in water or melted, the ions can move and the solution or melt conducts electricity. These ionic properties are completely different from the contrasting properties of the metal and the non-metal that we started with. So to summarize, when 2 atoms approach, they have the possibility to bond if there is space in their outer electron shells. Non-metallic elements will tend to form self-contained small molecules, giving rise to volatile solids, liquids, and all gases. That's molecular covalent bonding. Compounds of carbon and silicon will give rise to brittle rock-like or polymerized giant structures, giant covalent bonding. Metallic elements will bond together to form metallic structures with loose electrons, metallic bonding. And if a metal bonds with a non-metal, we get ionic compounds with properties totally different from their elements, ionic bonding.